Welcome back. So we're going to pick up talking about transformations with another example. Here, my transformation is designed, it's specifically written as, notice, a matrix A, which is given right here, times a vector V. And notice I'm taking vectors that have 2 components and taking them to vectors that have 3. So we are going to use this. And let's just start off with the same thing. If I give you the vector 2, -1, what would be T of U? I want you to try this now that we did an example previously. Go ahead and pause the video and find that T of U. All right, if you did that, you probably did, that's just our matrix A times 2, -1, using what we know about matrix multiplication. That's 2 times the first column plus -1 times the second column. So we end up with 5, 1, -9. All right, hopefully that makes complete sense. All right, let's go to a different question. This question would be, if I have a vector, is there a vector V such that TV equals B when B equals this? In other words, what I'm asking is this, here's a different way to think about it, is that in the range? That is my question. There could be multiple vectors, I don't care. I just need at least one for which that works. Again, we're not going to guess that, but what that means is I'm looking for A times some vector V equals my given vector, or I'm looking for this augmented matrix to solve it. So go ahead and, again, we've already done this, so I want you to pause the video and I want you to solve this augmented matrix right here. Go ahead and do your row operations and reduce that. All right, so if you went ahead and did that, row operations, I would take care of row 2 by 3 times row 1, subtracted, boom, we get this. And then you could take row 3, notice -1 and 1, so just add them together, that goes away. Resetting, I have this. Well, I can scale real quickly row 2 because it's all, if I wanted to get it all the way down. If you wanted, you could have just done it by 1/7 and not had fractions, it doesn't really matter. In any case, with the 1, I can then just say, okay, what's 4 times row 2 and subtract that from row 3, and notice it gets me exactly where I want. Now this, here's a key thing. Notice this row, it does not have any leading coefficients. However, each of my columns does. Because each of my columns, when I'm in row echelon form, has a pivot, it means it has a solution, and specifically one solution. If I wanted to take a step further, I could actually add up, so I get row reduced echelon form. And this right here actually tells me that my vector is actually this. And by the way, that's the cool part, is my vector would only be the first 2 components, not all 3, because it only would have 2 entries in it. So we got exactly that. Boom. All right, so we answered that question. So if I want to know if something's in the image, I can work with that. All right. Is there more than one V whose image is my given B? That's a question that we had. So we already found one value. Is there another one? So going back, I'm going to come back to this matrix. Again, because I had an entry in each of my columns, I have a leading entry in both my columns, 2 columns, 2 leading entries, I have no free variables, which literally tells us the answer to this question, which is no, there is only one V, the one that we've given, whose image is that V. So because we had 2 pivots for 2 columns, we're good. All right, now here's another interesting one. Is this in the range? This is another way of asking the exact same question we did before, but for a new B. Now I'm doing this because you will get asked the same question multiple different ways. It's a key thing about being fluent in our different concepts in math, is that we realize that many questions are actually the same question just verbalized in multiple different ways. And so understanding our ability to interchange them is a key part of what's sometimes referred to as mathematical maturity. Or personally, I call it mathematical malleability, the ability to flex into different situations. So I want you to figure out, is that in the range based on what we just did for the previous example? Go ahead and pause the video and try it. All right, so if you did this, again, we're just trying to solve this system, except I have a new, notice I just changed out, so I now have a new value here. So we're now trying to solve this augmented matrix. Go ahead and go through your steps to solve that augmented matrix. Hint, they're going to be the same. Go ahead. All right, so one of the things that we can do here is literally we can solve it like this. And then for the second one, again, we do the same steps. And notice the only difference is, again, that third column, our augmented column, is the only difference. If we take this new matrix, and obviously we can still scale this, except this time I want to scale row 3, just because I didn't want a fraction, but I could have scaled row 2, and I could swap them, and then I could just add, I wrote, wow, that was a typo. So this right here should be row 2. My brain was thinking 7. Anyways, if I do that, notice at this point in time, we have this. This is a problem. Whenever you have all 0, so I have no leading coefficients, but I have a non-zero entry, there is no solution to that. So that literally means that my matrix, my vector I just had a second ago, that this vector is not inside my range. So because I got a row with zeros and then non-zero in the augmented part, it's not a solution. All right, last question on this one. Is it linear or not? That is really, really hard, except it's not. So what's T of CV? Well, that's A times C times V. But by our matrix properties we already talked about, boom, the C goes on the outside and the A comes into the V, which is just C times TV. Again, T times U plus V is just going to be A times U plus V. We know we can distribute the A, which is just T times U, T of V plus T of U. So it is linear. And in fact, this is where we can get some general notes. One, a matrix transformation is just like the one we already did, where as long as, notice, its number of rows corresponds to where is it going, its columns corresponds to where is it coming from, and it's always linear. Matrix transformations are always linear equations. Well, that's really, really useful to know. Further, the range is the set of all linear combinations of the columns, and the range is in other words, the range is the span of the columns. So again, this is where linear combination and spanning come back in. And we love that because that's really, really important as we go forward. And in fact, we will get to this in chapter 4, and we'll call this our column space. I'm doing a spoiler alert here. Now, also, I will note that a linear transformation will always take the 0 vector to the 0 vector. Now, by the way, that does not mean it's the only one that takes the 0 vector to the 0 vector. Again, there's a specific term for that. Now, the generalization is that T of all linearity, we actually can do this not just for 2 vectors, but for any set of vectors. And this is an idea that actually goes into what's called superposition from engineering and physics and so forth. So the general idea is it will take lines to lines and triangles to triangles. And if any of you are like, what about squares? Well, squares are 2 triangles together. So we only care about lines and triangles. Now, I will give you a couple of different transformations that they're good to know, not huge impact at this point in time. One is called a shear transformation. It's a linear transformation that takes a square and turns it into a parallelogram. So if all of you are trying to figure out visually what that looks like, it means I take a square, that's not a perfect square, and it turns it into like a rhombus kind of thing. So I'm going to turn into some kind, now all it has to be is some linear transformation. And the key parts about it is there's more pictures in your book, but the idea here is to take sides, and corners to corners. So your sides always end up as sides, and your corners always go to the new corners. This right here is an example, is if I did the matrix, so R2 to R2, using the matrix 1, 0, 1, 1, that actually will, and you can try that, create a square, use all the points as your vectors that you're inputting and see where they go. Now, one other thing to talk about are what are called dilations and contractions. They literally are scalars. So I just notice I'm going from the same space to the same space. All I'm doing is I'm scaling them. If that scalar is between 0 and 1, it's called a contraction. In other words, it just takes the length of every vector and shrinks it down. On the other hand, if R is bigger than 1, it stretches it out, so it's a dilation. Again, these are not hugely important for the sake of this class, but they do have massive implications when we are attacking various different ideas and applications. Please let me know what questions you have. Good luck.